Okay. So we're assuming that if you're in this class, you probably know what a polynomial is, but in case you don't, we define a polynomial p of x to be cn times x to the n plus cn minus 1 times x to the n minus 1 all the way to plus c naught. And here cn through c naught are can be complex numbers, but for this class, we'll generally confine them to reals and mostly integers. C naught through Cn are known as coefficients, and xn, x to n minus 1 are terms. Well, Cn times x to n, dot, dot, dot. We call a real number, a complex number z is a root of p of x, if and only if p of z is equal to 0. And we denote the n as the degree of the polynomial, or degree of p. So the fundamental theorem of algebra is one of the most important theorems we'll be dealing with. And it states that counted with multiplicity, a polynomial p of x has exactly degree p roots. So in the above example, it has n roots. And I suppose most of you already know this. And if p has roots z1 through zn, then it can always be factored in the following form. And we will be talking about this later. So our first topic today is going to be Vieta's formulas. So do you guys know what Vieta's formulas are? You can type in the chat. Okay, it seems like most people do, but some people don't, so we're going to review them. So recall from the previous slide that all polynomials can be factored in the form c of n times x minus z1 times x minus z2 times dot 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 times x minus zn. But oftentimes we don't find polynomials in this form. We find them expanded, like an xn plus an minus 1 xn minus 1 plus dot dot dot. So, but just because they're expanded like this doesn't mean that we can't factor them. It just means that they're not appearing as factored. So if we factor them as an times x minus r1 times x minus r2 times dot 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 times x minus rn, we can actually expand the right-hand side and find a naught, a1 through an explicitly. So how we do this is we just expand the right-hand side normally. So if you look at the x to the n on, how do we take notes with all the, Isabel, could you explain? Sorry. Also, like, we're gonna have one person talking at a time, so please direct your questions to people who aren't talking at the moment.
William, I don't think they're able to do that.
Oh, they aren't?
Yeah, they're only allowed to send it to the host, I think.
No, I think they can send.
We're co-hosts. They should be able to send to us.
Then don't send to William. If he's talking.
Yeah, okay. You guys can send to co-host. So please send to co-host.
Yeah, no. You guys can send to co-host. It's fine then.
Yeah.
So anyways, continuing, if you compare the x to the n term on both sides, we have like an x to the n. We have an is the coefficient of xn on the left and the right. But that's obvious since we defined it to be that way. But it gets more interesting if you look at, say, the x to the n minus 1 term. So on the left-hand side, the coefficient of x to the n minus 1 is an minus 1. Can somebody tell me what the coefficient of x to the n minus 1 is on the right-hand side? Oh yeah, I guess when I'm asking questions, you should probably send to me. Okay, I guess we have an example on the next slide to explain this. So let's instead of looking at general n, we'll look at n equals 3. So p of x equals x minus r1 times x minus r2 times x minus r3. Can somebody factor this? I mean, can someone expand this for me? Yeah, as a lot of people have been typing in the chat, we have that P of X is going to be equal to X cubed minus R1 plus R2 plus R3 times X squared plus R1 R2 plus R1 R3 plus R2 R3X minus R1 R2 R3. And the reason for this is just straight expansion. If we look at the X squared coefficient, if we want to choose, we can think about choosing two X's from the three terms, and then the third one we have to choose negative Ri for I equals 1, 2, and 3. And then same thing for the X term, same thing for the X to the 0 term. And as you can see, this makes the coefficient of X squared negative the sum of the roots. The coefficient of X positive the sum of all possible two products of the roots, and the coefficient of X and naught negative the product of the roots. So if we want to extend this in general, we have Vieta's formula, namely that, oh yeah, I let an equal 1 in the previous example, but in this case, when an is not 1, we just divide everything by an. So in this case, we have that the sum of all the roots is going to be equal to negative an minus 1 over an, because on the right-hand side, the coefficient of x at n minus 1 is going to be negative r1 minus r2 minus r3 all the way to minus rn, all times an. And then similarly, we have the same result for an minus 2 over an all the way to the product, which is going to be negative 1 to the n times a naught over an. That was a bit fast. Are there any questions? Okay, so somebody asked me to explain it again, so I guess I'll do that. I just found out I can write, so I will write. So if we look over here, when we look at x to the n minus 1, if we just straight expand it, okay, somebody says I am making this more complicated than it is. I probably am. This is just straight expansion though. I think that I've made myself clear enough, have I? Okay, somebody recommends me say that Vieta is like a relationship between roots and coefficients, and yeah, that's exactly what Vieta's formulas are for. So I guess this will be made more clear in our the questions later, but when we're trying to find things about our roots, particularly some symmetric sums of our roots, then Vieta's can be very useful. So I think we've made ourselves clear enough over here. Let's get to some examples then. I cannot scroll. Okay, so here's going to be our first question. 2008 AIME 1, question 7. So I'll give you guys some time to digest this. And if you guys have any ideas, you can feel free to message them to us in the chat. We'll get a running list of a few possible ideas to solve this question. Okay, somebody said that the first thing we should do is expand what we have right now. So maybe expand this ginormous thing. So if we do this, this is a surefire way to solve the question. Because once we expand it, we can express a lot of, basically everything in terms of Vietas. But this is probably not a good idea because we're going to have a lot of terms. And as a lot of people have been saying in the chat, what probably is a better idea is to notice that there is no x squared coefficient, which means that the sum of the coefficients is 0. I mean the sum of the roots is 0. So what that means is that r plus s cubed is actually equal to negative t cubed. So we can use this instead, and this completely avoids expanding. Because now instead of expanding, instead of needing to expand, we find that our sum is negative r cubed plus x cubed plus t cubed. So at this point, how do we finish? So a lot of people are typing answers in chat. I'm actually not interested in an answer right now. We want to know how to do it. Okay, some people are also saying Newton sums. This is a good idea, but we haven't learned Newton sums. Okay, a lot of people are saying to expand r plus s plus t cubed. This seems like a good idea, but it's gonna get very messy very fast. So what we can do instead is consider the definition of a root again. So the definition of a root is that if you plug it into the polynomial, you get 0. So in this case, if we plug in r, we have 8r cubed plus 1001r plus 2008. And it's going to be equal to 0. So how does this equation help me? One moment. Yeah. How does this equation help me? Okay, so people are telling me to rearrange it. We can do that. So we get negative r cubed is equal to 1001 r plus 2008 all over 8. Can anybody see how to finish this question now? Yeah, exactly. We, instead of doing this only for r, we plug in s and t, and then sum all three of them. So what this will give is negative r cubed plus s cubed plus t cubed is equal to 1001 r plus s plus t plus 2008 times 3 all over 8. and then since we know that r plus s plus t is equal to 0, this is just going to be equal to 2008 times 3 over 8. Which, as a lot of people have said in the chat, is equal to 753. So hooray, looks like that's our answer. Do we have any questions about this question? Somebody says they don't get the last bullet. So what we're doing is that in our second to last bullet, we have an expression for only r. But what we're doing now is that we're summing, we have the exact same expression for s and for t, since r, s, and t are all roots. So when we add all three of them together, we get the left-hand side is negative r cubed plus s cubed plus t cubed, and the right-hand side is 1001 times r plus s plus t plus 2008 times 3 all over 8, since we're just adding fractions. We're then using r plus s plus t equals 0 again to get our final answer. So some people may be wondering that the fourth bullet looks a bit like magic because the only reason this works is we don't have an r squared coefficient. So if we want to find the general equation then of r cubed plus s cubed plus t cubed, I think some people have noted, have talked either about Newton sums or the identity, a very useful identity, which I'll type in. This formula is by no means necessary for this question, but I think one moment, is loading in. Yeah, the last bullet. It's a very good formula, which you guys should know, but it's by no means necessary. But it does help solve this question very fast. Okay, if there are no questions, we will be moving on to the next question. Okay, 2013 HMMT algebra number 5. Once again, we'll give you some time to think about this question before we get going. Once again, you guys can type ideas into the chat. Okay. So now that you guys have had a chance to read, some people are saying that we should find M, N, and P in terms of A and B. And this is a pretty good general strategy because in the end, we're concerned with only A and B, and well, only B. And M and P are not that nice. So our general strategy will be to express M, N, and P in terms of A and B. So which one of these is the easiest to express? Yeah, a lot of people are saying P. So P is just going to be equal to negative r squared s squared t squared by Vietas. But we know that RST is equal to 1. So P equals -1. Okay, that seems pretty good. Are there any, so which other one is easy to express? Okay, people want to express M next. So once again, by Vietas, we have that M is equal to negative R squared minus S squared minus T squared. So to express this as in terms of A and B, we see that R squared plus S squared plus T squared is equal to R plus S plus T squared minus 2 times RS plus ST plus RT, which is equal to A squared minus 2B. So this means that M is going to be equal to 2B minus A squared. So now I guess the hard part is finding N. Does anybody have any ideas to find N? Okay, yeah. So people are saying that we should square N. I mean, we should square B. So to find M, we squared A, so it makes sense when we find N to square B. So if we square B, we find that B squared is going to be equal to R squared S squared plus R squared T squared plus S squared T squared. That's what we want. But then we also get some nasty terms. And if you factor them, you get that the nasty terms is equal to 2RST times R plus S plus T. But this is good because we know that RST is equal to 1, and we know that R plus S plus T is going to be equal to negative A. So what we get out of this is actually that N is going to be equal to B squared plus 2A. So now we have expressions for M, N, and P in terms of A and B. So I guess now we can just find G of -1 directly in terms of A and B. So we know that G is equal to -1 plus A minus, -1 plus M minus N minus 1, which is equal to -2 plus 2B minus A squared minus B squared minus 2A is equal to -5. Okay. And let's clean up this expression slightly. So now we have A squared plus 2A plus B squared minus 2B minus 3 is equal to 0. So how do we finish? So just as a reminder, we're trying to find the maximum possible value of B. So why can't B be as large as we want it to be? It's because if it's too large, then there's not necessarily a value of A such that we can have there's not necessarily a real value of a such that the left-hand side is equal to 0. But as people are saying in the chat, we're going to use trivial inequality on this one. So what that means is that we're going to complete the square. And this gives that a plus 1 squared is going to be equal to, so if we complete the square, we get a plus 1 squared plus b squared minus 2b minus 4 is equal to 0. Okay, and now what this means is that we have to have that b squared minus 2b minus 4 is less than or equal to 0, or else there's going to be no value of a. So b squared minus 2b minus 4 is less than or equal to 0, and you guys know how to solve quadratic inequalities. This just gives that b has to be less than or has to be between the roots of the quadratic. So b is less than or equal to 1 plus square root 5. So our final answer is that the maximum value of b is 1 plus root 5. And we also need to check that this value is achievable, but as our work shows, this is pretty clear. It's achievable when a is equal to -1, since then the last equality is 0 plus 0 equals 0. So are there any questions on this question? Somebody asked, what is trivial inequality? This just means that a squared is greater than or equal to 0. Well, x squared is greater than or equal to 0. So if you look at the last equation, we have that a plus 1 squared has to be greater than or equal to 0, which means that b squared minus 2b minus 4 has to be less than or equal to 0. Okay, looks like there are no other questions, so we're just going to move on. I'm going to pass the mic over to Brian.
Okay. Hi. Okay. Yeah. So next we're gonna. So before we just looked at like the coefficients of the polynomial, and like so there's kind of in a polynomial there's kind of two important sets of information. There's the coefficients of the polynomial, which tell you some things about the polynomial, and then there's the factorization and the roots of the the factorization of the polynomial that gives you other information, right? So we just talked about the coefficients and how, in particular, how they relate to Vieta's formulas and the roots. But now we're going to focus more on the roots and look at just the factorization itself. Okay, so let's start with a problem, I guess. So this is 2016 AIME 1, number 11. Yeah, so just like think about it for a bit, and then if you have ideas, you can like send them to us, I guess, or something.
Oh yeah, guys, please type to Brian now since he's gonna be talking about this question.
Yeah, so a lot of people are trying to plug in x equals 2. And so while this does like help with while this does give you a relation between p of 2 and p of 3, this doesn't really give you that much information about the polynomial as a whole, right? So in, so that does so it's a good first idea, but it doesn't actually give you that much. So instead, you want to think about the factorization of the polynomial and its roots in particular, right? So, well, we can find roots by just setting one of the sides of the equation equal to 0, right? So yeah, this is done by plugging in -2 or 1, right? And so yeah, so what does that give when you plug in -2 or 1? Uh, yeah, good. So a lot of you guys are saying, yeah, so you can get that -1 and 1 are both roots of p, essentially, right? So now this is pretty useful information, right? Because um, you can, well, this allows you to basically, uh, well, given this, you can plug in more values of x that gives you more roots of p, right? For example, you can plug in -1 or 0, and either of these will tell you that p of 0 is also 0, right? Some of you guys have been saying that as well, right? Yeah, so yes. So yeah, for example, we can plug in -1, right? So if we plug in -1, well, then we see that on the right-hand side, we have p of -1, which we already knew was 0, right? And then on the left-hand side, we get -2 times p of 0, right? But the -2 we can get rid of because the right-hand side is 0, right? So then this just tells us that p of 0 is also 0, right? So now, well, we we know 3 of the roots of p, right? So what this allows us to do is this allows us to factor p in the form of some polynomial, let's say q of x times x minus 1 times x plus 1, right? Uh, if you want me to, so like for example, we, that should be an equals, but you can essentially, q of x is just any uh any polynomial, right? So then and well, this, if you write it in this form, this basically can encapsulate all the information of plugging in any of -1, 0, or 1 will give p that is 0, right? So well, now we put this back into the original equation, right? And so well, we want to see what that does to well, what remaining information we can get out of this polynomial p, right? Because eventually we want to find p of 7/2, and well, as it is, there's not much, like there isn't really enough information until we can figure out what q means, right? So yeah, so we plug in that, and then well, we see that all the x terms all just cancel out, right? All like on the left hand side and on the right hand side, we both get x minus 1 times x plus 1 times x plus 2, right? So all of that stuff just cancels out, and so we're left with q of x plus 1 equals q of x, right? And so, well, this is actually very useful, right? Because well, yeah, this just tells us that q has to be constant, right? Because if we think about it, well, q of 0 has to equal q of 1 has to equal q of 2 has to equal q of 3, and so on and so forth, right? But then, so q of x minus q of 0, for example, just has infinite solutions at all, infinite zeros at all of the at all integers, right? So it has to be exactly 0. So q of x just has to always be the same value, right? So, well, what does this tell us, right? Well, we go back, so we can write it as q of x equals c for some c, right? Well, now we remember, so this is all the information that we can get out of that first equation, right? But we still remember that we have the second equation that we haven't done anything with, which is that p of 2 squared equals p of 3, right? So now is like a great time to try to use that equation, right? Because we have p of x down to a single constant, essentially, right? So all we have to do is just find out what that constant c is, and then we'll be done, right? So we try plugging in 2 and 3 into p, right? And then so we see what we get. Right. So when we plug in p of 2, well, we see that p of 2 is equal to 6c, right? No, is the thing not working? We're having some technical difficulties right now, but I'll just say it in words, I guess. So we get that p of 2 is equal to 6c. I guess I can say it in chat, right? I can send it to everyone. So we get p of 2 is equal to 6c, and we get p of 3 is equal to 24c, right? So, well, this tells us that 6c squared equals 24c. And, well, we remember that p is also non-zero, right? So this means that c is non-zero. So this tells us that c is equal to 2 over 3, right? Because you just get like c is equal to 24 over 36, which simplifies, right? Okay, there, now it's working. So yeah, now we plug in 7/2 into this, right? Because now we have uniquely identified what p is. P is 2/3 times x minus 1 times x plus 1, right? And then so we plug in 7/2 into that, and then I think we get, what do we get? I think we get 35 over 4 or something. Wait, no, 105 over 4, right? Yes, 105 over 4. So, yes. And well, now we just have to find 105 plus 4, which is just 109, and then that's their answer. Okay, so are there any questions on that? Okay, so I guess we'll go on to the next question. So yeah, this is the next question. So I'll give you a few minutes to think about it, gather ideas, and then we'll start discussing it again.
Once again, you should be chatting with Brian, not me.
Okay. So yeah, so there, a lot of you guys are suggesting Vieta's formulas, and well, this will work, but I would not recommend it because in general, Vieta's formulas gets uglier the more variables you have and the higher degree it is, right? So basically it will be a bit of a, like, it will be kind of bashy, and then you kind of don't want to deal with that stuff, right? So instead, I saw a few people suggest another idea, which is you see the x1 squared plus 1, x2 squared plus 1, x3 squared plus 1, x4 squared plus 1. And well, you kind of recognize that as being somewhat similar, I guess, to um, kind of the expanded to what you get if you would plug in something into P of x, right? Like if you would plug in something into P of x, then P of x is also equal to x minus x1 times x minus x2 times x minus x3 times x minus x4, right? So if you want to just kind of turn it into something so that, well, you want it so that the those x1 squared plus 1, x2 squared plus 1, x3 squared plus 1, x4 squared plus 1, you want it so that all the four of those terms would be linear, right? Because if they're linear, then, or you can convert it into the product of linear things, well then we can get it pretty nicely, right? So, well, we see that, well, although it looks like it's a sum of squares, it's actually also the difference of squares, right? Because if you think about it, uh, x1 squared plus 1 is also just x1 squared minus negative 1, right? And then so this gives you x1 plus I times x1 minus I, right? And then you can do the same for all the other three terms, right? So I guess, how do we get this equation? So we remember that P of x is, so I think this was discussed on the slide a few slides back, which was all polynomials, if they have roots R1 through Rn, then uh yeah, so that bottom equation there, that would be how you would get that that equation of when you plug in like P of C, that equals C minus x1 times C minus x2 times C minus x3 times C minus x4, right? Because Cn is 1 in this case. Right? Oh yeah, we probably should not have chosen C. Well, can you change it to like X or something? Or like Z? Because C is already used in the problem.
Yeah, my bad.
Yeah. But yeah, so anyway, yeah, thanks for that. Yeah, so we can we write it all as just x1 minus I times x1 plus I times x2 minus I times x2 plus I times x3 minus I times x3 plus I times x4 minus I times x4 plus I, right? And then this equals, and then we use the bullet 2 to get p of I, to get that equals p of I times p of negative I, right? You're also plugging in z into p of x, but yeah. Yeah, so does everyone see how that works, right? And then from here, you can just plug in I and negative I into the original polynomial, right? Yeah, also, William, if the second bullet point should have z plugged into p of x instead of c.
Yeah.
Yeah. Yeah, so now we just have to plug in I and negative I into the original polynomial p of x, right, in as its expanded form. And then we get that, so we first find p of I, and p of I is 1 minus b plus d plus c minus a times I, right? This is just like using I and the fact that I squared is -1. Right, yeah. And then p of negative I is like basically the same thing, except you flip the signs of the AI and negative CI terms, right? And now, well, we look at this and then we recognize that it's basically the difference of squares, I guess you can say, right? Because it's, you have a real part, which is 1 minus b. It's like a number multiplied by its conjugate, essentially, right? Because it's 1 minus b plus d is the real part for both of them. And then you have a minus c and c minus a are the two imaginary coefficients, right? And then so essentially, well, you just use the fact that this is like a difference of squares or whatever, and then you see that that equals 1 minus b plus d squared plus a minus c squared, right? And then, well, from here it's pretty easy, right? Because you now just have to maximize this given that b minus d is greater than or equal to 5, right? So, well, the first term is at least 16, right? And then the second term is at least 0. So then the minimum value that it can take has to be just 16, right? And then, so this is, I mean, if you were to actually fully solve it, you would also have to find a construction, but we'll leave that to you guys. It should be doable based off of like the inequalities that you have, right? Because essentially you need that b minus d has to exactly equal 5 and a minus c has to exactly equal 0, right? And then, yeah, I'll leave that as an exercise. So yeah, I guess, does anyone have any questions on that? If not, I'll pass it to Aditya, I guess.
As a side note, you can also use this strategy on the last problem we did, the HMMT one.
Oh, yes.
Yeah, it's just Vieta bashing is a lot more feasible with the degree 3 polynomial than degree 4.
Yeah, yeah. In general, like as the degrees get higher and stuff, everything just gets uglier. So if it works for degree 3, it won't necessarily work for degree 4. But yeah, okay. It doesn't look like anyone has questions, I don't think. So I'll pass it to Aditya, I guess.
Okay, so now we're going to be discussing the remainder theorem. So the remainder theorem says that when you take a polynomial with real coefficients and you divide it by x minus c, so the remainder for that is p of c. So all of the problems in this section are not actually going to really use the theorem, but we're going to use the general strategy in the proof of the theorem. So first when we divide it by x minus c, we can write the quotient as q of x and the remainder is r of x. So then we can say p of x equals x minus c times q of x plus r of x. So then, so the degree of q would be the degree of p minus 1, so that when you multiply q by x minus c, you get the same degree as p. And the degree of the remainder has to be less than the degree of x minus c. So the degree of the remainder, r, is just 0. So that means that r of x is a constant function. So if we plug in x equals c into that initial equation, p of x equals x minus c times q of x plus r of x, the first term on the right side drops to 0. So we get p of c equals r of c. And now since the remainder is a constant function, the remainder is always equal to p of c. So this is basically like a strategy we're going to be using. We're going to try plugging in roots of our of what we're dividing. So first, a problem from intermediate algebra. So I'll give you guys a few minutes to think about this one. Send me your thoughts, I guess. Okay, so a few people are saying to factor that cubic, x cubed minus 2x squared minus x plus 2. So yeah, we're gonna factor it first. So I guess by the rational root theorem, we would want to check the roots plus or minus 1 and plus or minus 2. So if we check x equals 1, that's a root. If we check x equals -1, that's also a root. And if we check x equals 2, that's a root. So we can factor that as, so yeah, we can factor it like that. So now we're gonna write it like, so now we're gonna divide our polynomial by x minus 2 times x minus 1 times x plus 1. So we're gonna use like the same setup as we did before. So we're gonna have that x to the 100 minus 4x to the 98 plus 5x plus 6 equals x minus 2 times x minus 1 times x plus 1 times q of x plus r of x. And okay, yeah, so remember in the previous slide when we had x minus c, we plugged in c. So we're going to be doing the same thing here, where we can plug in 1, 2, and -1. But first, I just want to note one more thing. On the previous slide, we said that the degree of r of x was 0. But here, the degree is not going to be 0 because we're dividing it by a cubic. So the quotient is going to have degree, so the quotient here is going to have degree 97, and the remainder is going to have degree at most 2, because all of the cubic terms can be divided out. So you're going to have, so r of x is going to be some quadratic, so we can write r of x equals ax squared plus bx plus c. So, wait, William, are you putting that? Okay, so we'll first plug in 1, 2, and -1, and we can get some values for r of x. So when we plug in these are our roots for that cubic, so that first term is going to be 0. And so then we just evaluate the left side, and that's going to be equal to whatever r is at those values. So r of 1 is 8, r of 2 is 16, and r of -1 is -2. So now, as I said before, we can write r of x equals ax squared plus bx plus c. So if we plug it in at these values, so r of 2 is 4a plus 2b plus c, and that's equal to 16. R of 1 is a plus b plus c, and that's 8. And r of -1 is a minus b plus c, and that's -2. So now we have 3 equations for a, b, and c, and 3 variables. So it should be straightforward to solve. So we can subtract pairs of the equations to cancel c, or and then we could also add the first and the last equation. Subtract the first and last equation to get b equals 5, and we can get a equals 1 and c equals 2. So that's the solution to this. So once we have those values, we know r of x is x squared plus 5x plus 2. So that's our remainder here. So anyone have questions? So someone asked, how do you get r of x? So r of x, we knew it had to be quadratic, or the degree was at most 2 because we're dividing it by a cubic function. So we're going to have a degree that's 1 less in our remainder. And so we just set it to ax squared plus bx plus c, and we plugged in the values to get those equations. So someone's asking how to get 8, 16, and -2. And so that's just if we take x to the 100 minus 4x to the 98 plus 5x plus 6, and we plug in 1, 2, and -1, we'll get those values. So we're plugging x equals 1. Okay. So I guess we'll go to the next question. Okay, so we have a polynomial with integer coefficients, and we're given 3 values, and we want the smallest possible value of p of 2016. So again, how do you send your thoughts about this question?
My head hurts.
Okay, so well, not that many people are saying anything, but so someone said to take everything mod 2016. And so I guess this is a good idea, but we're gonna, so when we do this, we're gonna actually just, so I think it's easier to find what n is and then take mod 16 at the end, mod 2016 at the end. Okay, so so someone is saying to divide it by x minus 1 times x minus 2. So that's so let's try that. So if we write p of x equals x minus 1 times x minus 2 times q of x plus r of x, so if we write that, then we have, so since we're dividing it by a quadratic term, we have r of x is linear here. And so now if we take, so r of x is linear, remember that. So now if we plug in x equals 1 and x equals 2 here, so x equals 1 gives p of 1. So p of 1 is 2. So we get r of 1 is 2. And when we plug in x equals 2, we get r of 2 is 3. So given that r is linear, what do you think r is? So I have two values of r. Yeah, so r has to be x plus 1 because we have these two values for it. So now we can plug in x equals 3 into this equation. And we get p of 3, which is 2016 on the left, and on the right we get 2q of x plus 4. 2q of 3 plus 4. So if we solve that equation, we get q of 3 is 1006. So yeah, solving this equation, q of 3 is 1006. Okay, so now let's see what happens when we look at p of 2016, because that's what we're trying to find. So p of 2016, if we plug that in, that's equal to 2015 times 2014 times q of 2016 plus 2017. Okay, so basically we need to find the smallest possible value of q of 2016 so that this number is positive. And so now we're gonna have, so actually we're gonna use a lemma. So we have this lemma here. So when p is an integer polynomial, which is what we have in the question, then a minus b divides p of a minus p of b. And so we can prove this pretty easily. So if we just subtract the two polynomials and evaluate them at a and b, we get so we get this. So p of a minus p of b equals cn times a to the n minus b to the n plus cn minus 1 times a to the n minus 1 minus b to the n minus 1 all the way to c1 times a minus b. And so you can factor out a minus b out of every single one of those terms. So a minus b divides everything because we know all the coefficients are integers. So this is gonna be this. So this is a pretty important lemma, and we're gonna use it in the problem now. So I guess so. We can, so the easiest way we can use this is, so we need to find Q of 2016. So we're going to apply it with Q, and we know Q of 3 is 1006. So we can write that 2016 minus 3 divides Q of 2016 minus Q of 3. So that's equivalent to 2013 divides Q of 2016 minus 1006. Okay, so this means that Q of 2016 has to be 1006 mod 2013. So, and we want to select the smallest possible value of Q of 2016 such that P of 2016 is positive. So I think it's clear that that value is just, Q of 2016 is just 1006. Because if we let it be a bigger value, then P of 2016 is larger. And if we let it be a smaller value, then it's negative. So we have to have Q of 2016 equals 1006. And so now P of 2016 is 2015 times 2014 times 1006 plus 2017. And so now we just have to evaluate this mod 2016. So as someone said, 2015 times 2014 is, so 2015 is -1 mod 2016, and 2014 is -2 mod 2016. So -1 times -2 times 1006. So that's 2012, which is -4 mod 2016. And if we add -4 to 2017, we get 2013. So this number is 2013 mod 2016. So that's the answer. So anyone have questions? Okay, so I guess I'll pass it on to Daniel.
Yep. Let's go on to the next problem. So we'll be doing this problem, which is just one problem of general set of problems which ask you to find, which give you a polynomial p that takes a bunch of, that takes a nice value for a bunch of different inputs and wants you to find p. So here we have a polynomial p that has degree 2015, and p of n is 1 over n squared for all integers from 1 to 2016. And we want to find 2017 p 2017. So I'll give you some time to think about this. Okay, so one suggestion I got was to write q of x is equal to px minus 1 over x squared. Now we know that this has zeros 1 through 2016. But the problem with this is that that px minus 1 over x squared isn't actually a polynomial. You have a 1 over x squared term, and that's not a polynomial. So, but we can fix that by just multiplying by x squared. X squared times px minus 1 now has lots of different roots, all integers from 1 through 2016. And we also know that since p has degree 2015, q has degree 2017. And we know that it's divisible by x minus 1 times x minus 2 all the way to x minus 2016. It has all of these x minus n's as factors. But we only have 2016 of these linear factors. But the thing has degree 2017. So we need to introduce an additional linear factor at time x minus k. So our general form is qx is equal to c times x minus 1. Yep, right there. So now we have this equation for q for x for px, but we still need to solve for the constants c and k. We don't know what they are yet. But we actually have two other pieces of information. The polynomial on the right-hand side is divisible by x squared. That means its constant term has to be 0, and the coefficient of x also has to be 0. So let's do the constant term first. The constant term is just c times 2016 factorial times minus k plus 1. We take all of the linear factors, take the x minus n, multiply all the n's, and find the constant coefficient. So again, in the end, that should be c times 2016 factorial times minus k plus 1. And now we know that this number has to be 0. The linear term, the coefficient of x, is a lot more bashy, but we can do it as follows. So we have 2017 linear factors on the right-hand side. So what we want to do is to pick one of the linear factors and take an x from it, and all the other linear factors give their constant coefficients. So for example, we can take 1 times 2 times all the way to 2016, and then times the x from the x minus k. Then we can try 1 times 2 times all the way to 2015, take the x from 2016, and take the k from x minus k. And then we can try 1 times 2 all the way to 2014, pick the x from 2015, take the 2016 from x minus 2016, and then take the k. And now when we sum everything up, the expression is 2016 factorial times x plus k times 2016 factorial. And then inside we can write 1 plus 1/2 plus 1/3 through 1 over 2016. And we'll let that be h 2016. So hopefully this will be a lot clearer when we have the equation up on there. It's probably easier to see why the equation works if we have it written down. Yep. But we note that the expression to the right of k is the product of all possible sets of 2015 of 1 through 2016. And we can write this as 2016 factorial divided by 1 plus 2016 factorial divided by 2 plus all the way to 2016 factorial divided by 2016. And now factor out 2016 factorial. So we'll use h sub 2016 to denote 1 plus 1/2 plus 1/3 through 1 over 2016. And that means we can simplify the linear coefficient greatly. It's c times 2016 factorial plus 2016 factorial k h sub 2016. And there's no plus 1 at the end of this one. The plus 1 only applies to the constant coefficient. Yep. So now let's try to solve for these for C and K. We have two equations for them, and now we just have to set them to 0. So for the first equation, we have C times 2016 factorial plus 2016 factorial K is equal to 0. 2016 factorial H 2016K. And that means K is equal to -1 over H 2016. And now that we know this, K is equal to -1 over H 2016, we go back to the equation we have above with the constant term being 0. That means 1 plus 2016 factorial over H sub 2016, C is equal to 0. And that means C is equal to -H 2016 over 2016 factorial. So let's just wait a little to get the equations up on here. So we sped forward a good bunch, but now that if we have the values of C and K, we can just plug in 2017 into the expression and get the answer. So we have some expressions for how to solve for C and K. I can type in the two linear equations into the chat. So this is the constant equation, and the one for the linear coefficient is and I'm just writing H to mean H sub 2016. Now, if we solve these two linear equations, well, they're not linear. We solve the second equation first because we know that C isn't 0. And the second equation implies that K is equal to -1 over H. And we plug this value of K back into the first equation, and then we get that C is equal to -H over 2016 factorial. Now we plug these values of C and K back into our original expression for Q of X. And then we can plug in 2017 to get the answer. If you do the substitution, a lot of the factorials and h's cancel out. And the final answer, we end up getting that 2017 times p of 2017 is just -H sub 2016. Someone was asking to go back to the previous slide. Can we get that? Yep. Yes, slide contains most of the important details. The other slide is solving equations. So we note that x squared px minus 1 has all the integers from 1 to 2016 as roots. Since x squared px minus 1 has degree 2017, that means we can write this equation for x squared px on the second line. We know that x minus 1 through x minus 2017 are all factors, but we need one more linear factor to make the degree 2017, and then we have an additional constant that can happen. And now we know that the left-hand side has a factor of x squared, which means that the constant coefficient and the linear coefficient on the right-hand side both have to be 0. So we set up equations to represent this situation. We solve them, and then we can get the values of C and K. So we can actually find out what the polynomial P is. And then we can throw in P n equals 2017 and extract the answer from there. So there are lots of different questions that give you a polynomial P, which takes a lot of nice values for a certain set of numbers and ask you to find the polynomial P or find P of some other number. And the general approach for these is to rewrite the given condition as P of, as something like, in this case, x squared P of x minus 1, as all of these given numbers as roots. And then we can write that this polynomial has a bunch of linear factors. And then there are a couple of coefficients that might change. We see that we have an extra linear term and a constant term out front, but then we can get some additional information from this equation and solve for the coefficients. So this determines the polynomial uniquely. So the top of the slide says Lagrange interpolation. Actually, given an equation like this, there's a formula to write out what P is. It's fairly nasty, and it can be very painful to slog through all of the calculations and get the answer. But for some problems, this might be the easiest approach, not this one though. And we won't explain the formula here, but we have a derivation and explanation on the handout that we'll post after class. So it looks like we're almost at 9 o'clock. We do have a couple more questions, so we will probably run over time a little, but if you guys need to leave, you can leave now. Yep, this question is
This
from
will
this
all
year's
be in the
AIME.
transcript, by the way, so like it's fine if you leave now because you can watch it later.
Yeah, these questions and their solutions will also be on the handout.
We actually have 2 more questions, but for time reasons, let's only do one. So we have this question from this year's AIME, which some of you may not have the best history with. And our other question is from the 2017 ARMO tiebreaker round. So which ones do you guys want to do? Poll in the next 10 seconds. Ooh, okay, fancy. Well, yep, it looks like it's overwhelmingly in favor of the AIME question. So let's do that instead. Okay, so I'll give you guys a couple of minutes to think about this. All right, so let's start off by, ooh, I hear a very big echo. Okay, so let's start off by writing P of x is equal to x minus r times x minus s. We know that the leading coefficient is 1, so there's no constant factor out front, and r and s are the roots of this polynomial. We do this because we want to know what the roots of the polynomial are, because we know what the roots of p of x are. Yep. So now, if p of x is equal to 0, that means p of x must either be r or s. So the roots of p of x are the roots of p of x equals r and p of x equals s. So now we actually have, we only need to consider two cases. We know that 3 and 4 are roots of p and p of x. They either have to be roots of the same quadratic, or they have to be roots of the different quadratics. So let's do the first case first. So suppose that 3 and 4 are roots of the same quadratic. So suppose their solutions to p of x equals r, say. That means their roots of x minus r times x minus s is equal to r. So a and b are the roots of the other quadratic. The roots of x minus r times x minus s is equal to s. So let's take a look at the first one. 3 and 4 are roots of x minus r times x minus s is equal to r. But if we look at Vieta's formulas, that tells us that r plus s is equal to 3 plus 4, which is 7. That's because the leading coefficient of this polynomial is 1. And the linear coefficient is negative r minus s. So by Vieta's formulas, we know that the sum of the roots of this polynomial is r plus s. But we know what the roots are, 3 and 4. So the sum of so r plus s is 7. But now if we look at the second polynomial, we notice that the leading coefficient is also 1. And the linear coefficient is also minus r minus s, which means that the sum of the roots of this polynomial is also r plus s. But we just found that r plus s is 7, which means that a plus b is also 7. And in this case, we get that a plus b squared is 49. So that was it for this case. When 3 and 4 roots of the same quadratic, a plus b squared has to be 49. So now we have the second case where 3 and 4 are roots of different quadratics. So suppose that 3 minus r times 3 minus s is equal to r, and 4 minus r times 4 minus s is equal to s. Then and suppose that a is the other root of x minus r times x minus s is r, and b is the other root of p of x equals s. So what we want to find here is a plus b, the sum of the roots of two different quadratics. So let's expand the equations we have listed right here. We know that rs minus 3r minus 3s plus 9 is equal to r, and rs minus 4r minus 4s plus 16 is equal to s. Now, if you look at these equations, we see that if we subtract them, we can cancel out r and s. We can cancel out the product rs. So if we subtract the two equations, we actually get r minus s is equal to r plus s minus 7. I'll wait for the screen to catch up. Yep. Well, 9 minus 3r minus 3s plus rs, and 16 minus 4r minus 4s plus rs. But yeah, so suppose we...
No, that's right. The r and s will just move to the other side.
What? Sorry. Oh, okay, I see. Yeah. Okay, yeah, well, let's subtract these two equations to get rid of the rs. When we do that, we actually get rid of the r's too. And we just get a single equation for s. And this equation tells us that s is equal to 7 over 2. Yep, and s is 7 over 2. Now this is super useful because now we can get r. we go back to the first equation, 3 minus r times 3 minus s is equal to, no, let's go to the second equation. 4 minus r times 4 minus s is equal to s. Now we know that s is 7 halves. So we plug that in and we get that 4 minus r is equal to 7. So r is equal to minus 3. So now this is super useful information. We know what r and s are. They're negative 3 and 7 halves. So we actually know what p is. So from here, it's not too hard to solve for what a and b are. So let's do that right here. So the sum of the roots of p of x is equal to r is should be r plus s. If you expand p of x is equal to r, x minus r times x minus s is equal to r. You see that the as before, the coefficient of the quadratic term is 1, and the quadratic coefficient of the linear term is negative r minus s. So by Vieta, the sum of the roots is r plus s, but we know what r and s are, so the sum of the roots is 1/2. That means a, being the other root of p of r is equal to s, is equal to 1/2 minus 3. And b, being the other root of p of x is equal to s, is going to be equal to 1/2 minus 4. So now that gives us that a is equal to negative 5 halves, b is equal to negative 7 halves, and now a plus b is equal to negative 6. So that means that in this case, a plus b has to be equal to negative 6, and the only possible value for a plus b squared in this case is 36. So now there are only 2 possible values for a plus b squared, 49 and 36. And when we add them, we get the answer of 85. We have a very similar problem like this on the problem set, so you should try that. Any questions on this one? I guess that's it for today then. We have an additional ARMO problem that we didn't manage to get to, but we do have a fully typed up solution on the handout that we'll post right after this. So you
Yeah,
can
so
look at
the handout is already posted on
cool.
the website, and
Yeah, I just sent the link.
yeah, and the link is in the chat. So yeah, this looks like it's the end for our first meeting. Excuse us for the slightly clunky technology. We're still trying to get it worked out. And if you guys have any suggestions or questions, feel free to email us at our email, youthconway@gmail.com. Feel free to stay after if you have questions. We're unmuting the chat.
Yeah, and we're also gonna post the recording and the transcripts on the website later.